Hello and welcome to Code It Yourself role-playing game part 2. If you've not watched the first video, you probably will need to. This is a direct continuation from that video. And if you remember at the end of that video, we ended up with Jario, oddly enough, from the platform game, walking around a map. And we can see here that Jario can't overlap with anything that's in the map that we're considering static. And what this video is going to be about is introducing dynamic objects, i.e. that's the things that move. Now you might be thinking, well hang on, we've already got a moving object, surely we've already covered that. Well, yes we have, but we now need to make it more general purpose, and we're going to use object-oriented programming to do that for us. In the most basic sense, anything that moves we can consider a dynamic object, but I'm going to extend this a little further, that anything that isn't static or background is going to be a dynamic object, and we'll see later on that this can involve event triggers and switches and teleporters and all sorts of things that make the game happen. Once we've got the very basics of dynamic objects out the way, we'll look at how we can script sequences to form cutscenes. We did actually describe what the dynamic objects were in the first video, and in this game I'm going to restrict them to being 1 unit wide by 1 unit high, and that equates to about 16 by 16 pixels. So all of our dynamic objects are going to occupy a single tile in the game, although they are free to move in a continuous domain, so we're not going to keep them locked on to particular cell boundaries. So let's start with the basics. We know that we're going to have a position for our dynamic object, which is going to be an x and y coordinate, floating points. We know we're going to need a velocity, which will update the positions depending on the elapsed time, so we'll call that vx and vy. We're going to have two Boolean flags. Determine the collision detection properties of the dynamic object. Is it solid against the map? For example, Jario can't walk through a tree or a building. However, things like a bird or a bat might be able to fly on top of things. So we don't always want things to be solid against the map. We'll also see later on that sometimes we want to adjust these properties very briefly to help us get some certain effects. We're going to check, is the object also solid against other dynamic objects? So if we've got enemies in the game, again, we don't want the player character to be able to walk through them, but sometimes we might. So we're going to keep these flags a bit separate. We're also going to record, is the dynamic object considered friendly or not? And we'll see later on that this will determine what on-interaction properties do we need to set. For example, if the dynamic object is friendly and it interacts with a friendly dynamic object, then probably it's a conversation or something interesting is going to happen. However, if one of them is friendly and one of them is not friendly, it's most likely the intention was an attack. So we'll want to handle this differently depending on the friendly state of our dynamic objects. And the way I'm going to structure the dynamic object is to have a base class, dynamic, and for things that move around and perhaps have their own behaviours, we're going to inherit from it and call it dynamic creature. And because we may want to specify the individual behaviours of a dynamic creature, this is where we're going to break it out into the different types of enemies. So for example, we might have a bat type enemy, we may have a skeleton type enemy, and we may also have friendly characters, so perhaps there's an NPC type. For things that aren't dynamic, we don't necessarily need to create an intermediate class, we can still just inherit from dynamic directly. So this may be, for example, a cell that teleports the player to a new location. It may be a signpost. So even though it's called dynamic, what I really mean is anything that isn't static or map. Doesn't necessarily mean it has to move around, it's an entity that we can interact with. At the end of the last video, we ended up with 3 main source files. We had the main application, which contains the onUser create and onUser update functions. And we also created a singleton class called RPG Assets, and this loaded a single instance of, well, basically the sprites. And we're going to add more things to this, so I think the maps are also going to be something that we'll want global access to, but we only ever want to ensure one instance of them exists. So we'll update this class too. We also created a map class, which basically stored the static information of the maps, and they were created via an external map editor created by this community. Currently, moving Jario around doesn't involve any additional classes. In fact, we just store the values for position and velocity directly in the main class. We're going to be changing this because the player object is indeed going to be a dynamic object too. So this means we'll have to make quite a lot of changes to our onUser update function to accommodate a new architecture. The good news is we've already got static collisions done. We'll just have to refactor it a little bit to suit the new architecture, but we'll also need to add dynamic collisions. So this is when dynamic objects interact or collide with other dynamic objects. On the whole, we're going to move this class away from the idea that there is one central dynamic object. In this case, it's Jerrio. Instead, we're going to maintain a list or a vector of many dynamic objects, and they'll all be handled independently. And we're going to rely on object-oriented programming to differentiate between the behaviors and interactions necessary for each object. Let's start by creating our base class for a dynamic object. I've added two files, rpgdynamics.h and rpgdynamics.cpp. I'm going to include all of my dynamics in one file, simply because it makes it easier for me to make the videos without having to skip between different files. In practice, however, you probably would want to separate all of the individual classes into their own files. So let's start by creating a class cDynamic. I'm not going to put the method bodies into the header file, I'm just going to prototype the functions. So we need the constructor, we'll put in a destructor too, and I'm going to add some public properties. So we know we need the position, px and y. We're going to have the velocity, vx and vy. And we're going to have the three booleans I discussed earlier. And we'll call that b solid versus map, solid versus other dynamics, and whether or not this dynamic object is considered friendly. I'm also going to include a type of string to name the dynamic object, and this is going to be very important for differentiating between dynamic objects of the same class later on. And it also becomes a game design element because it will be easier for the people writing the script for the game to work with objects that have sensible names, and we've done that for the sprites already. String isn't declared yet, but we'll come back to that in a minute. Now I'm going to add some base methods. And these are going to be overridden, so we're going to exploit inheritance and polymorphism a lot in order to facilitate the different behaviors of the object. So we'll start by creating a virtual function, and this means it is our intention that we're going to allow this function to be overridden. And this one is going to be called drawSelf. So the object is going to be responsible for deciding how it looks on the screen. And so to do that, I need to pass to it a pointer to an instance of the OLC console game engine. And if you remember from the first video, we modified it slightly to be object-orientated in its own right. So I'm going to just call that pointer graphics. We'll need to include the console game engine at the top of our class, of course. Now the console game engine does some naughty things. One of the things it also does is include string and sets the namespace. I'm sure you'll have plenty to say about that in the comments. One thing that's also important for the object to draw itself is it needs to know what the current global offset is of the screen, i.e. the camera position. And this is because the object will only know where it is relative to the world coordinates. It won't know where it is relative to the screen coordinates, so we need to provide this offset. Now, this function for the base class doesn't need a body. I could set it to be pure, which would make this class abstract. But in this case, I'm just going to leave it with a blank pair of braces. The second function I'm going to add, again, is going to be a virtual function, and it's going to be update. And this is where the object can update itself using the felapsed time provided by the game engine. Again, by default, this is going to do nothing, but you might be able to start to see where this is useful. Let's assume this dynamic object later down the line is a bat. During this update function, the bat will want to fly around, and this will allow us a facility to do this. I'm going to allow the dynamic object to be named via its constructor, so I'll just put in those parameters. So for our base class cDynamic, the dynamic object, all we've got are the two methods left to fill in. One is the constructor and one is the destructor. Right now the destructor doesn't need to do anything, but the constructor does need to specify what the name is. And we'll also take advantage of this opportunity just to initialize all of our variables. Now I'm going to assume that all dynamic objects to begin with are solid versus the map. And I'm also going to assume they're solid versus each other. It is likely that most of the dynamic objects created are going to be things that we don't want to walk through the scenery. And I'll also assume everything is friendly. What a great place. What you may have noticed is nowhere in this class have we provided a facility to know what the dynamic object looks like. At this level of abstraction, that's unimportant. So let's start using the dynamic object system for the player character. I'm going to inherit now a new class called CDynamicCreature. And I want to inherit publicly from our base class. And what this means is anything that's declared public in here will remain public. As usual, we've created a new class, we're going to have to create a constructor for it. And this time I'm going to pass in the name, but I'm also going to allow us to start using the assets. So for drawing this particular creature, we need to give it a sprite pack so it knows how to draw itself. We also need to provide implementations for the draw self and update routines. So I'm going to copy those from up here, put them in down here, get rid of the virtual keyword. You could leave it there, it doesn't make any difference really. Get rid of these braces, but I'm going to use the override keyword so it's clear that we've overridden them. But because this is an inherited class, we can give it some variables of its own. So I'm going to create some that are protected. In particular, I want to store a pointer to the sprite that we're passing through. And I also want some additional properties so we can assess the state of the creature. And we'll assume, because it's a creature, that it's alive. So this is where we can start thinking about some game variables. So we'll have health as an integer, and we'll also have max health. So consider if this was the player character, this would represent how much health they've got left, and this represents how much health they can possibly have. So if they use some item that restores health, we know that there is a maximum it can be restored to. Of course, we'll also have to give bodies now to the new constructor. So here it is, dynamic creature, constructor is taking the name and the sprite, and I'm going to use this notation to say, but also please call your base constructor, which will set the name for us, and default the variables. So the only thing we need to record now is the sprite variable, and we're going to set a default health and max health value. We're going to say we'll have 10 to begin with, and a max health of 10 too. So the creature has full health at the start. Later on, we'll probably want to overwrite these with different values for different creatures. We also need to provide the update function and the draw self function. And I'm just going to use a line of comments here so we can see that there's some separation. This is why it might be useful to do things in different files. So here I've got the base class, and here I've got the derived class dynamic creature. And this is where we can start to have a little bit of fun. I have decided in advance of a format and layout of a sprite sheet for all creatures. And it looks like this. Here we've got individual sprites, which are 16 by 16 pixels. And I'm using this sprite viewer that the community created. We can look at them individually. But we'll see the first column is the sprite walking downwards. You can see the animation in the top right of the image. The second one is the sprite walking towards the west. Then we've got north. And then we've got east. We've got some additional ones. This is the sprite celebrating, and this is the sprite dead. Now the artist that created this sprite pack has also included two more, which is just standing facing and standing facing away. For this series, we won't be using these two. But what is important is that all of our creatures in the game follow the same sprite format layout, because we're going to let the dynamic creature class handle which sprites need to be drawn given on the status of the creature. So for example, in this case, we've got what we're calling Sedit slimes, created by Sedit on the Discord server. It's the same thing, so we've got walking towards the player, walking towards the west, walking away from this player, walking towards the east, and we've got a celebration and a dead slime. And additionally, again, a skeleton character this time, exactly the same states of animation in the same locations. And this is quite important. Knowing that all creatures are going to be drawn with the same sprite layout means we can use some tricks. So I'm going to use an enumeration here to store which direction the player character is facing. I'm just going to hard code these in as 0, 1, 2, and east is 3. And I'm going to store this as facing direction. Now if you haven't seen this notation before, it's really I've just done an enumeration in a single line, and I've basically at the same time declared this mn facing direction variable as having the type of this enumeration. So this means we can apply, instead of 0, 1, 2 and 3, we can apply south, west, north and east as the facing direction, and the compiler will be completely fine with that. I'm going to have exactly the same for other states, so standing, walking, celebrating or dead. I'm going to store that as graphic state. So if you remember, south, west, north and east tie up with which column of the sprite sheet we're going to be using, and depending on what the dynamic creature is doing, we'll choose whether it's standing, walking, celebrating or dead. In the constructor, I'll just default these. So I'm going to say the facing direction is south, and by default it's doing nothing at all, it's just standing there. Just going back to the sprite editor again, I can see a walking animation. Well, it's probably about 1/5 of a second between me pressing the up and down keys. So this means the dynamic creature is going to need to keep track of time to know which particular frame of animation to play. So let's add that in. I'm going to create a floating point variable which will just accumulate time. And of course, I'll also need to add that to the constructor, set it to 0. And this is where we'll start looking at the update function. So every 0.2 of a second, I want the sprite displayed to change. Now fortunately, the game engine provides us with how much time has elapsed, so we just add that to our ftimer variable. And when the ftimer variable gets beyond 0.2 of a second, I'm going to subtract 0.2 of a second from it. So this means we get a consistent period of time, irrespective of what the rest of the system is doing. And we'll come back to that in just a little while, but let's set some of the graphic states that are fairly obvious. So if the dynamic creature's health is less than or equal to 0, we're going to assume it's dead. That's the sprite that we want to display. If the creature has any velocity components at all, it's moving. So we'll set it to the walking state. So here I'm just looking at the absolute values of the Vx and Vy components. Of course, if it's not walking, it's just standing. The final state, celebrating, we'll probably look at in the next video when we start to add some of the finishing touches to the dynamic object classes. We also need to determine which direction the player is facing, and we can do that based on the velocity component. So if they're negative, it's facing west or north, and if they're positive, it's facing east or south. Now the draw self function for the creature needs to choose the sprite that is suitable for the state of the creature at this point in time. So I'm going to create two variables, sheet offset x and sheet offset y, which are indexed into the sprite location. So in the top left here, that's sheet offset 0, and we go all the way over to celebrating, that's sheet offset 4. And of course in the x direction, and if we've got a 1 sheet offset in the y direction, we've moved down to the next row of sprites. So I'll use a switch block to determine, based on the state, how we set these variables. If the creature is simply standing still, the only property that matters is the facing direction variable. On the contrary, if the player is dead, then we want to specifically choose a sprite location to display, because there's only one option. Walking, on the other hand, is a little bit tricky, because we've two to choose from, depending on the state of mftimer. So this implies we need an additional variable, which I'm going to add an integer called mnGraphicCounter. Again, in the constructor, I've defaulted this to 0. I'm not going to show this each time. From now on, I'm going to assume that you understand that it's important to give your variables a default value in the constructor. And essentially, this variable that we've added is going to oscillate based on the time, and we're going to use this variable to select which row of the sprite sheet do we need to display to the player. So every time we get this event on every sort of 0.2 of a second, I'm going to increase the counter by 1, and then I'm going to make sure it doesn't go out of control by modding its own value with 2. So this will oscillate between 0, 1, 0, 1, 0, 1 forever, which means we've got two variables to choose our walking sprite from. In the x direction, it's the direction the object is facing, and in the y direction, it's that oscillating counter, graphic counter. You can see I've got multiply by 16s in here because this is going to give us the pixel coordinates in the sprite sheet. All that's left in the draw self function is to actually get the creature to draw itself, and because we've passed in a pointer to the console game engine, we can use the draw partial sprite function to do just that. But you'll see I've also included the offset variables. And that's because the dynamic object exists in world space, but we need to draw it in screen space. Unfortunately, there's a one-to-one translation because all of our cells were 1 unit by 1 unit. We just need to take into account where the camera is looking in world space. And the sheet offset x and offset y variables will give us the top left of a particular tile in our sprite sheet, and we know it's always 16 by 16. Of course, it's undesirable to have 16 hard-coded into the game engine. You'll see it everywhere at the moment. If we do want to move to higher resolution or indeed lower resolution in the future, we should probably make this a constant somewhere, maybe even in our RPG assets class. For now though, I'm going to hardcode it in because to me it helps me visualize that this offset is one full unit of pixels in our game space. So let's just have a little recap of all of that. We've got a sprite sheet which is carefully laid out to be usable by the game engine. If we don't obey the rules of the sprite sheet, none of this code will make any sense. In the update function, we're determining what state the dynamic creature is in. At its most basic, is it walking, is it standing, or is it dead? And in the drawSelf function, we use that state information to decide which sprite of the sprite sheet to extract in order to draw on the screen. Let's now go back to our main file and include the RPG Dynamics files we've just created. And instead of hard-coding in a dynamic object like this, we're going to use our new framework. But I'm not going to create a creature outright. What I'm going to create is just a C dynamic. And I'm going to call it MP Player for now. So it's a pointer to a dynamic object that's going to represent the player. Just for those thinking ahead, we will be changing this a little bit later on. I'm going to use a polymorphism now to take our C dynamic player object and from that create a new dynamic creature object. Which needs a name, and we'll call this one player. And it also needs a sprite, so we'll use our singleton that's managing the assets. Get sprite, and there's a sprite also called player with a friendly name. And you'll see the compiler has no problem with this. Even though MP player is of type C dynamic, we're basically telling it actually you're of type C dynamic creature. This of course now gives us lots of things we need to change in order to facilitate moving the player around the screen. We're no longer handling these things directly. So wherever we saw position and velocity before, we now need to make those relative to our new pPlayer object. So in this case it's going up, it's Vy. And down, Vy, and left and right, use X instead. We'll also start to see some leftover junk from the Jario platformer. We're no longer choosing the Jario sprite based on anything that's going on here. The object itself will choose its own sprite, so we can start to clean this up a little bit. And I'm also going to take this opportunity to start making this a lot more generic. So where we've got variables that are specifically indicated as player position X and Y, they're just going to be new object position X and Y instead. So for example, in this case, I'm going to change it to new object position X. And instead of using sort of the player here, I'm going to just simply use object and choose the px value. I'm going to create a temporary dynamic object, or a pointer to one, which points to our pPlayer type. And the reason for this is later on I'm going to have a big collection of dynamic objects and I want to perform the same code. Right now I'm hard coding it for the player so we can test all of our animation code. I'm going to go now through all of the code and make these changes. Right, I always by default want the camera to follow the player object, so here we will use it explicitly. And this is where we're going to always need access to a variable that represents the player object. So even though the player is bundled in with a bunch of dynamic objects, it's always useful that the player has some sort of priority access. So here I'm going to set the camera to its position in the X direction, and here I'm going to set it to the Y direction. So I've just gone through and updated all of the static collision code to handle a generic object, although in this case the generic object is hard-coded to be the player. The only thing left to change then is how it draws itself. Well, we've already drawn the map, so once we've drawn the map we then want to draw the object. And instead of just drawing the player, it's going to be drawing all of the dynamic objects later on. So we'll try and keep this as generic as possible. Instead of drawing the object using the draw partial sprite routine, we'll get the object to draw itself using its drawSelf function. And so we just need to pass a pointer to the console game engine, so I'll use the this keyword for that. And we need to pass in the camera offsets, which is much tidier. And this is where we'll start to see some of the power of object-oriented programming, is we've really quite simplified this now. The object hides the nasty code full of constants and things to make things appear on the screen. And this same code will be for all of the objects that are considered dynamic. When we created our player, the constructor of the dynamic creature just specified 0, 0 as the location. I'm going to hard code this to a more sensible number so the player is in the map. So I'll pick a number. Let's say he's at location 5, 5. Right, so that's been a big lot of code. Let's see how it goes. So we can see the player character is in the map, and we're moving around like Jario. What we don't see is any change in sprite. All we've done is successfully replace Jario for Witty. That's the name of this guy. And that's because at no point have we called the update function on the player character. So at some point we're going to need to call the update function for the dynamic object. And I'm going to do that before we specify any camera control code. It feels like the right place. And it's just calling the update function with the f-elapsed time. So let's take a look now. Well, good. The character is starting to walk in the right direction. He's facing the right way at least. And he is indeed walking, but it's very fast. And this is where we're going to have to start thinking about some of the game design elements. He's clearly moving too fast for his walking animation to make much sense. So where we were specifying the velocity to 10, I'm going to set it to 4. And that's much more sensible. Very nice. Now we've got maps and we've got at least one moving object, we can start to have a little bit of fun. Let's start thinking about cutscenes. Let's start by making an assumption that the cutscene only controls the player object, given that that's all we've got so far. So we've got a dynamic object, which represents our player. But let's say we want to move the player to a certain location, present some dialogue, move to another location, present some more dialogue, wait for a minute, do something. There's a sequence of events that we can perform in order to facilitate plot and give the game some atmosphere. So we might want the character to be able to walk to a different location. So we know that that is some sort of command that we're going to need. We may want the character to simply just wait. So let's add some parameters to these two. So if we're going to walk to, we know that we're going to have an X and a Y. If we're going to wait, we know we're going to have some duration in seconds. Let's say we want the character to say something. Well, we probably want to show some dialogue. There'll be some sort of text. What we need is a program within a program. And the way I'm going to do this is to create objects which represent commands. And a queue of these commands is sent to what I'm calling the script processor. And whenever the script processor has something to do, it stops player input. And surprise, surprise, we're going to use object-oriented programming to handle all of this for us. So I'm going to need a basic class called command. And commands are going to be temporarily in control of something until the command has been completed. So I'm going to create a flag completed. And I'll add two methods to this command. Start, which starts the process of the command happening. And as usual, we'll have update. In case the command takes a certain amount of time, we need that time to elapse. So this will also then take f elapsed time. To implement a cut sequence, we'll queue up a sequence of commands. This queue is fed into the script processor. And the script processor will then go and control the game engine. So if this queue is empty, the script processor has nothing to do. It's not in control of the game engine. In which case, presumably, the player is in control of what's happening. So the script processor will also stop player input. And for all of the different commands we want, we're going to subclass ccommand for the individual implementations. So for example, a wait command, we might want it to count the f-elapsed time before we can set it as being completed. For the move command, we'll probably want to pass in a dynamic object for the command to take control of whilst it moves it to the location it needs to be. And once it's reached that location, it's completed. So each time the script processor determines that a command has been completed, it removes it from the queue and the next command gets put in place. Once all of the commands are finished and the queue is empty, control is given to the player again. I appreciate with my simple scribbles on the screen, this is quite a complicated idea to express, but the code itself is quite simple. So let's do that. As before, I've gone ahead and added rpgcommands.h and rpgcommands.cpp. Here is our basic command class. it does nothing of any function. All it's doing is defining the interfaces which subclasses of this will use to implement what the command should be doing. Let's create another class, our script processor, which implements the theatrics. And before we get to adding any interface functions, we know that the script processor has a queue of commands, and I'm going to use a standard list to implement this. We also know that the script processor is going to govern whether or not the user, the player, has any control. So we'll have a very accessible flag to deny the player control if necessary. I'm going to add two interface functions. The first is add command, which is simply going to add an instance of a command to the list. And the second is process commands, because commands are a temporal thing. They're not just a single event. It takes time for a command to walk a dynamic object from one location to another. So a command doesn't just happen instantly and it's finished, it takes a duration. So let's add the simple ones first. We've got a constructor for our script processor, and we've got add command, which is just going to push the pointer to a command object to the back of the list of commands. The important one is the process commands function. We're going to call process commands every single frame. That's why we're passing elapsed time with it, because some commands are going to require that duration. This means we can also choose whether or not to enable player control on a frame-by-frame basis, and we'll do this simply by checking, is the command list empty? If it is empty, then the player has control. There's no commands to interfere with that. If there's anything in the list, we'll deny the player control because we're going to assume some sequence of events is taking place that hasn't finished yet. So if the list does contain something, we need to do something. If it's not empty, let's check to see if the command at the front of the list has been completed yet. If it's not been completed, then whatever's at the front, we want to call the start function on. That will cause one-off initialization. In fact, it actually won't, because right now this is getting called every single frame, and so that means this start function is also getting called every single frame. So I'm going to modify the base command class to have a Boolean flag which indicates whether the command has been started or not. And this is one of those times where it's much easier to work this stuff out in code rather than with a pen and paper to begin with. So along with our completed flag, I'm also going to have a started flag. So because I only want to call the start function once, I'm going to check the started flag before I call it. So here we've got, if the list is not empty, that means a command is available. If the command at the front of the list has not been completed, check to see if it's been started. If it's not been started, then start it, and this will only occur once, so this becomes an event. If the command has been started and it's not completed, it's a command currently in process, so we want to call the update function instead. If in the situation that the command at the front has been completed, we want to delete the command because we're going to pass it in as a pointer, and we're going to remove it from the front of the list. And right now, this is all our script processor needs to do. It just maintains access to this list and calls the start function or the update function as necessary by the sequence. So let's go and create our first command subclass. And I'm going to call it moveTo, which is going to walk a dynamic object from its current location to a target location. And so I'll create a constructor for this, which takes in that information. So the first thing we do is take a pointer to the dynamic object, and remember this can be a creature, it can be anything at all, because as long as it inherits from the base class, all we need to do is pass that pointer in. The compiler will sort the rest out for us. I'm going to take a target X and Y location in world space, and I'm also going to say how long should it take for that operation to occur. So if we want the dynamic object to move quickly, we'll set a short duration. If we want it to walk there slowly, we'll set a long duration. We're also going to override the start and update methods of our base class. Now what's important to note here is that the class itself is going to take control of the object. So we need a whole host of private variables for this one command to facilitate a linear interpolation from the start location to the target location. So let's add some private variables. The first is going to be the dynamic object itself. We're also going to take the starting position, X and Y. We're going to set the target position, X and Y. And we're also going to store the requested duration and the time passed so far, because we're going to interpolate between the starting position, the end position, by calculating the time so far over the duration. you'll notice we've got some squiggly red lines under the dynamics. So we need to include RPG dynamics in our file. Let's go and add some body to this. So for our command move to, the constructor is going to take the target position and set the time so far to 0. For the duration, and just to make sure that the user doesn't enter inappropriate durations, I'm going to take the maximum between the duration specified and 0.001 of a second, i.e. 1 millisecond. And this is important to avoid a divide by zero error later on. I also, of course, need to store a pointer to the object that's being controlled. Now, why haven't I updated the start positions here? Well, simply put, I don't know where the object will be when this command is called. That's why we have the start function. If I've got a sequence of movements, I need to make sure that one movement has finished before the next, so the object's location will have changed. If I just specified the object's starting location as soon as I created the list of commands, well, it will have captured the object's position at that time I created the list, which could be different to when this command is called during the execution of that list. So the start command happens once and says, take a snapshot of where the object is now, and this could be at a point in the future. And so it is in the update function that we implement the linear interpolation. And this is going to be a standard linear interpolation. I've done videos on linear interpolation before. I'm not going to go into the details. Essentially, we take an accumulation of the current time divided by the overall duration. That gives us a normalized value, and we use that normalized value in effect to choose a point on a line between the 2 points, which I'm going to do here. I'm also going to specify the velocities, which is simply the amount of distance expected to be covered over that duration, because speed equals distance over time. Once the expected duration has expired, we make sure that the object is precisely where it should be, because the linear interpolation may be somewhere really, really close, but it might not be precisely. So I'm going to set it exactly, I'm going to set the velocities to 0, and I'm going to set the completed flag to true. This command has now finished. And so on the next process commands update, the script processor will identify that this flag is true, reject this command, and move on to the next one if there is one. So let's try this out by hacking something into our main file. Firstly, let's include the commands file. And I'm going to create a single instance of our script processor called mscript. To test the theory, I'm going to hard code a little script in place whenever the user presses the Z key. So we'll look for that event. So if the Z key is released, we're going to add some commands to the script processor's queue. So I'll take mscript, add command. Now, our command is the base class command, but of course we can use inheritance and polymorphism to actually specify the command that we want adding to this queue. And this is where polymorphism can be really strong, because all of these commands are going to be different objects, but this queue is quite happy to contain them all. And because we've got a common interface between these different objects, they can all have different behaviors. Now we know it takes a pointer to a command, so I'm going to have to use the new keyword, because we know that the script processor also deletes and cleans up the commands once it's done with them. So in this case, it's a move to command, and the object that we're going to move is the player. And for the first command, I'm going to move the player to 10, 10. And I want that to take 3 seconds. Once it's moved there, I'm going to move it to, we'll move it 5 across and keep it on 10. And then I'm going to move it from 15 to 15. And then we'll move it back to the start location. So it doesn't really matter what it's doing, it's just going to take control and move the player around for me. Script processing has to take priority over anything else. It's going to decide whether the player has input or not. So that's going to be the first thing I'm going to do in onUserUpdate. And the reason we want this at the start is because the current command might disable user input. So we'll check for that. If it's allowing user control, then we can allow the checks for the different keyboard commands. Let's see how this works. So now I've got control over the player. You can see I'm walking him around, and if I press the Z key, the engine is now in control. I don't have any further control. I can press the keys, it doesn't matter. But we can see it's executing the script, so the character is walking out a small triangle. And now I've got control again. So if I press Z key, the first thing the character does is move to 10:10 in 3 seconds. Then it was 15:10, then it was 15:15, and then it goes back to 10:10 again. And the nice thing is, all of the walking animation and everything else is all being handled for us. So even though we've added a completely different method of control, the game engine itself is sorting out what's necessary behind the scenes to facilitate the type of animations we want. Okay, so we have a single command, move to, and we have a single dynamic object, creature. Let's make the code handle multiple dynamic objects. I'm going to store my dynamic objects in a vector. And in the onUserCreate function, I'm going to create a few more. So I'm going to create a couple, and we'll just call them Skelly1 and Skelly2. And they're not going to use the player sprite. We want them to look a bit different. So let's have a look in our assets file. What have we got? Well, we've got one called Skelly. How convenient. So let's give it the Skelly asset. And I want to manually, for now, position these somewhere in the scene. So I'll set one at being at 12:12, and another one being at 5:8. Of course, these aren't called mPlayer anymore, they're something else. In fact, we can temporarily create them here as a CDynamic ob1 and CDynamic ob2. And what I'm going to do is add these to the vector, and I'm going to start a convention that the player object is always element 0 in this vector. So I'm going to push back the player first, and then I'll do the other two. And this is a little design convention which we'll see is quite useful later when we're starting to implement a quest system and handling maps full of different types of dynamic objects. If we always know where the player is, then that can make things a lot easier later on. So of course we need to handle things a little bit differently now. We need to put all of our update code for objects in a loop. And we'll use an auto for loop for this, where each object is going to be called object. And that's going to go through our vector of dynamic objects. I'm using the ampersand at the start because chances are I'm going to be changing the properties of the object in this loop. So I can get rid of that now. And let's follow this down to here. So all of our objects get subjected to the same static collisions with the maps, for now. I also want all of the objects to draw themselves, so I'm going to copy that and use it again down here. So let's take a look to see if object-oriented programming is helping us already. And we can see, yes it is. I've got two objects on the scene now, two skeleton enemies, and what we can see is, because the player is always the first object in the list, the player is drawn behind everything. This may be undesirable. I always really want the player to be drawn on top of everything, so the human player can always see the player character. I'm going to fake this, and this will cause some concern amongst some of you, simply by drawing the player object directly as the last thing that gets drawn. This may seem a little bit wasteful, because we're already drawing the player once. We could adjust this loop to ignore the first element of the vector. But what we're starting to see form out of this is the game engine is taking shape. It doesn't really matter what the objects are, they'll look after themselves because they've been encapsulated in other objects. The game engine just treats them all in the same way. So let's add a command to move one of these other objects. Let's take ob1. So we know it's already at position 12:12 to start. So in between our character walking around, let's add another move command for object 1. And we don't know that it's going to be called object 1, so we'll use the element at index location 1 of our vector. And we'll move it from 12:12 to, I don't know, we'll say, yeah, 15:12. And we'll say 2 seconds for that move. Now you might be thinking, this seems a little bit of an uncomfortable way to choose which object to operate on. You'll see later on that we can use the friendly names to decide which objects are moved around the screen, making it a little bit easier for the game designer. So if I press the Z key again, it starts our automated sequence. Player character is going to 10:10, then 10:15, and then object 1 has moved as well. And what's really nice is because we've got an established way to handle animation, when the object moved, it had the appropriate animation applied to it. We've had to do no additional code, even though it's a different type of object. So let's wrap this video up by adding one more command, and that's going to be to display dialogue on the screen. And I'm not going to line by line it, but I'll explain how it works. So we'll create a subclass of command called showDialog, and this is going to display text to the user. And the way it's going to work is each line of text is going to be specified as an element of a vector. And you'll notice we're only specifying the start function to be overridden. Let's have a look at the body for this. Well, the constructor just takes a local copy of that vector, but the start function needs to do something a bit special, because it's the game engine responsible for drawing things. And this is where we're going to need to start having some communication between the commands and the game engine. When we moved the objects, that was a communication between the commands and the object itself. In the game engine file, I'm going to create a function which is for displaying dialogue. showDialog, and it takes again a vector of lines. But we also need some additional properties to handle the showing of dialogue. We're going to store the dialogue that's being shown, and I'm going to create a Boolean flag that says whether there is dialogue on the screen at the moment. And this is quite important because dialogue is one of the only commands that we don't have any computer control over. The human player may take longer to read the dialogue than you might expect, and we don't want to specify a fixed duration that it's on the screen for. So instead, what we're going to do is show dialogue until the user presses the action button, which in this case is going to be the space bar. Of course, one option could be just to freeze everything until the dialogue has gone away, but then if there are any background animations taking place, they would also be frozen too. So it's important that we somehow cache the dialogue information and respond to it in a real-time way. So all our showDialog function is going to do is take a snapshot of the dialogue to show and set this flag that we are indeed showing dialogue on the screen. Now, I don't want to just render empty text to the screen. I want it to look like it does in an RPG game. So I'm going to create another function called displayDialog, which is going to handle drawing the dialogue in a pretty way. And this is probably going to be the first instance of where I'm just going to be putting code into this game engine, but not talking through it in detail, mostly because it's not very interesting. So really all this function is going to do is draw a background rectangle of a size appropriate for the dialogue that's been given to it. Now, because each line of dialogue is a separate element in the vector that's passed to it, I can work out how many lines of dialogue are displayed on the screen by looking at the size of the vector. I can then iterate through each element of the vector to work out what's the longest line of text. So that gives me an X and Y dimension for my box. The box is going to be a blue rectangle with a white border, and that's what all of this code does. But it draws the white border sort of 1 pixel offset around, and it knows the size of the font that we're using in order to draw the box to the correct dimensions. Then it's just simply a case of using our already created drawBigText function from video 1 to put the text inside that dialog box. I don't feel at this stage in the video series that it's necessary for me to go line by line talking through all of these little calculations. And it's this sort of detail I'm going to be omitting going forward. But I will encourage you to study the source code once I put it up at the end of this video series. So dialogue in some respect is quite unique, that it requires user interaction. And we also don't want it to be drawn on top of. So the last thing that we display, if there is any to show, is we display some dialogue. So I'm going to call our displayDialog function with the vector that's currently caching the dialogue to be displayed. Now, because the dialogue display is a little bit of an oddity, we know that the scripting engine has denied us user control, so we need to slightly break this. So even though the script engine is in control, there is one event that we want to look out for. And this event only applies if showDialog is true, because we're showing some dialogue on the screen, and we're going to respond to the spacebar being released. And when the spacebar is pressed, we no longer want to show any dialogue on the screen. Simply no longer showing the dialogue is not enough. I need to inform the scripting engine that this command has been completed by the user. And to do that, I need to artificially tell it that its current command has been completed. Which means I need to add another function to the scripting engine, completeCommand. So let's have a look at the script processor class, and we can add in another one, completeCommand. Let's go and give it a body. And the complete command function will allow us to prematurely finish the command that's currently in operation. So if there is anything in the list, whatever's at the front of it, we're going to say you're completed, whether it has or it hasn't. It allows us to externally stop the command that's in action. And this might be useful for not just dialogue, but perhaps maybe you've got cut sequences where things are dragging on or whatever. We can get the player to say, I've had enough of this. You can press the spacebar and the next command starts to execute. So going back to the actual show dialog command itself, when the start function is called on that command by the scripting engine, we need to call the show dialog function of the game engine. And to do this, I'm going to use a static variable in the command base class, which makes the game engine available to all of the commands. So let's see how we implement that. So here is our base command, and as you can see it has no functionality, but I'm going to add to it a static variable which is a pointer to our main game engine. At the moment that's called OneLoneCoder RPG. Now the problem is I can't just go and include OneLoneCoder RPG, because then we've got OneLoneCoder RPG including dynamics, including OneLoneCoder RPG including dynamics, etc. You start to get a bit of a problem. What I'm going to do is forwardly declare the game engine itself. And all I need to do is specify class OneLoneCoder RPG, and that tells the compiler that this symbol exists before it's reached by this line. You can see it's quite happy to accept that. However, it doesn't exist really. All we've done is shut the compiler up. We do actually need to give this some sort of implementation. So let's go into our CPP file. We know these are only compiled once. And right at the top, I'm going to include in here the actual definition of this variable. And it's a pointer, and I'm just going to initialize it to null pointer to begin with. Again, the compiler is happy with this, but it won't be, because there's still no body. What we can do here now is actually include our original file. And because we've included rpgmain.cpp up here, what was originally just an empty symbol has now been given a bit of a body. And so when we go back down to look at the subclass command show dialog, we can see that the gengine variable is now populated with all of the public functions that our game engine possesses. Meaning that this command can now access some of the utility from the game engine, in this case to show the dialog. However, at some point we need to initialize this variable to actually point to the game engine. And we'll do that at the start of onUserCreate. So here's onUserCreate. We're already creating our singleton and doing static things like that, so this seems like a good place to also define the gengine variable. So we know it's in our base command, gengine, and we know it's a pointer, but it's a pointer to this. Now I don't want to set a precedent here of creating what's called spaghetti code, where we've got all of these arbitrary links between classes. That is a bad design pattern, and we won't see this really again now as part of the game engine. But what we have allowed is all of our commands access to all of the utilities in the game engine very simply. So let's go back to our scripting sequence here, where we've just moved the skeleton object. Let's add in a new command, and this command is going to be show dialog. And remember, it takes a vector as the input, so I'm going to have, it's a skeleton, it might say something like grrr for the first line. And let's do a dual line one this time around. I think oop is really useful. There we go, let's make it appropriate for the moment. So our script will now move the player, then move one of the enemy objects, display some dialogue on the screen, and then move the player again. Let's take a look. So here I've got control over the player. I'm going to start the scripting sequence. So the player moves to the starting location. It's executing his first command. Now we're moving the enemy object. The enemy object has called the command show dialog, and we'll see we've got no user control, but everything has stopped. There's no more sequencing going on until I press the spacebar. And we can go through the dialog. And then the sequence carries on as normal. And I'm back in control. So one final thing, we can see when we're creating scripts we're getting a lot of code which is very similar, and we don't want to have to type it out over and over again. In this instance, I would suggest using a macro. So at the top of this file I'm going to declare a macro simply called x. And it takes an argument n. If you didn't know, yes, you can pass arguments to macros. And we know that in this case the code looks like this. mscript.add command new C command, and then there's an underscore. But then we want to use some macro syntax to concatenate the string that is n to that command. Wrap the whole thing up in a bracket and we're done. So if we go back down here, what I can do now is get rid of all of this and simply replace it with x and open brackets. And you see it's quite happy there. We've created our own little scripting language inside of another program. And so that's all for this episode. In the next episode we'll look at how we can combine scripts and sequences with quests, and how we can get everything to glue together to start forming the basics of an RPG. If you've enjoyed this video, please give me a big thumbs up, have a think about subscribing, and I'll see you next time. Take care.